Hello. So, what are we doing today? Everyone remembers the research paper we were writing, right? So these were the was the first draft that we wrote during the writing a research grad stream, and these are the different results we were able to obtain. So basically, we obtained results on the loss versus iteration, and for conventional and unconventional and training for CIFAR 10 dataset. Other than that, we also obtained our results on the interpretability, or you can say the how the internal layers are working. Interpretability was obvious from the train and well losses because the layer wise training allows us to look at the loss that has been reduced by each layer. So we can see that these two layers were reaching their saturation pretty fast. Right, there is it. Yeah, so it was very clear from the graph itself that the layer was training allows us to dig deeper into the network. So it is a really great technique when you're using it for architecture design, right? Because while we can clearly see here that the first two layers are reaching a saturation period really quickly and they are not able to really go too deep on the loss in the training losses themselves. Same for the validation losses. But after the introduction of third layer, we can see there's a drastic decrease and the training losses. Now, in this case, the validation also reaches a somewhat equal value. So here we can comment that, okay, this is working for us. So it is not overfitting the data. We can make that statement from this. Just give me a second. Huh. Hello. हाँ तुम पे हाँ हाँ बाइक तो नहीं मिल पाई नहीं नहीं oh no, I shouldn't have deleted that. Wait. I'll have to check the stream now. Use many filters so that there's no noise. I hope those filters are not removed. Hello, hello. Yeah, it is working. Sorry for the interruption, but yeah, where were we? So basically, when we introduced the layer-wise training technique, hello ChatGPT, what's up, bro? Good to see you here. Vivek, it was right, your name. So we were just discussing that the losses, the iteration versus losses curve allow us to see in a layer-wise training how the introduction of different layers allows us to better interpret the network layer by layer and how each layer has contributed into the reduction of losses. And that can also tell us if a layer is bringing some kind of overfitting or something. For example, if we are using a kind of network that introduces inputs from after some layers into a middle layer, into an intermediate layer, if the inputs are introduced into an intermediate layer and we see that there is some kind of data leakage or we want to prevent against that, we can clearly see that introduction, the layer at which the introduction of new inputs was there, the loss has drastically decreased there for the training, but it's not the case for the validation. So we can clearly say that okay, this layer is introducing some kind of overfitting, maybe we are causing some kind of data leakage by introducing some kind of inputs and we need to look into it. So these are the different benefits that are provided when we use a loss facilitation curve for a layer wise training network. So yeah, so this is all of what we have done. This is what the paper started with. These were the different results we obtained. So basically, the important results for us at that time also were training and validation losses for the conventional training, then the training and validation losses for our unconventional training, and the subjective results, which basically talks about how introduction of this layer-wise training also allows the layers to have a better intermediate understanding of the images. So you can see that in a traditional layer network, the oh my god, I don't know why word does that. That's so annoying. So you can see clearly in a layer-wise training method how the input image uh, is converted after even the first layer. You can clearly see the cars really barely visible after the first layer itself, and most of the features are not handled very carefully. So a lot of data might be lost by doing this. So this is how a traditional method works. And why is this happening? Because my insight on it was that when we are training the whole network simultaneously, the first layer only gets inputs according to the second layer, right? The weights of the first layer change according to how the second layer behaves and how the output layer behaves, and the first layer is never able to work closely with the output, final output that we want from the network. So basically, the first layer is not able to learn much features. But at the same time, if we look at the features of our layer-wise training, you can see that most of the features are even retained. Even till the second layer, you can still see kind of the ship forming here. And in the second layer, in the first layer, it is like completely apparent. Not much features are lost. And this makes the network more human readable in a sense that it is more, it this layer wise training might be more in touch with the how humans perceive data in a sense, because you know when humans work with something, we kind of retain these features and we try to understand the feature according to that. Now it is still very far off with how we work. Like our brain works on a slow plus fast thinking method where we have slow thinking for analytical thinkings and fast thinking for intuitive purposes and all of that craziness. But in a sense, if it is more human readable, if it makes more sense to humans, that means it is much more sensible. Whereas this network is learning from complete noise. This is something purely computational. This is not what we can understand. We can't see this image and say it's a car, but the computer can, because it is distributing those weights according to it. So this means the computer is trying to do some kind of overfitting into the algorithm of this particular data set, right? Whereas this method is much more human readable, which means that if we are able to read it, it means that the computer is doing something more sensible in terms of humans, right? There's that. And we were also able to see the same results, like the horse is clearly visible in some of these images. The features are not lost because this is layer wise training. So yeah, this is what we managed to discuss the previous time when we wrote the first draft of this paper. Now after that, when we started with the series of um, uh, our series of working ahead with our research paper, right, continuing on our research paper, working on our research paper, we saw that these results are not enough, as they are not proving uh, on a real test case how the greedy wise layer is helping us. So basically, we introduced a new test for it where we read our research paper. Uh, if you remember, we read a research paper on what we call a metal surface detection task. That is a real mechanical engineering task that allows us to automate inspection and quality management in factories. So that we saw, and we used those paper. We replicated the model, the CNN model they used for that paper, and we wrote all of this code. So yeah, so basically the last time we ended the stream on our research paper, we were not able to get our results. We were facing some errors. So I went through it, I solved those errors. So basically, one of the first things that you can see is that I implemented this class augmented dataset. What is this? So basically, in the paper, they talked about a lot about the different augmentations that they are using for their model. So in the previous video, I implemented those augmentations with the help of a PyTorch augmentation, right, the Torch augmentation library. But the problem with that was that it was not actually increasing that size of the data set. It was just randomizing it. It was creating an augmented data set, but in a sense, the size of the data set remained the same. So to solve that error, I basically wrote this class function. In it, what we do is we use an augmentation factor as an input, right? And we create a random seed. Okay, it is also important. We will come to it later. But what we do is whenever we are asked of a augmented index that is larger than the original index, it 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 would be calculated. And by using that, what we'll do is we'll pass that augmented index into our apply augmentation method, and we'll basically use a random seed with the help of that augmentation index so that we have a different random seed for different operations. And what this will allow us to do is that one index will have a specific value because of that random seed, but that specific value would be some randomization of these different flips and augmentations that we'll be applying on our image. And this augmented index would be used for later calculations. So we are basically virtually, you can say, increase the size of the data set, which is the definition of augmenting a data set basically. So that's what we were able, that's one of the change, right? The augment dataset class. Other than that, I also the error that we were facing basically, so the CUDA was getting run out of memory all the time, right? And we were not able to figure out what was the problem because everything we wrote was right. So we checked everything, we checked our classifier and all of this stuff, right? Okay, sorry. So we did all of that, but we were not able to find our error. So the error was actually that it is a very interesting error actually. So what we were doing was when we were using the GPU, right? So when we were sending our inputs, the images and labels to the model, we were basically converting them to we were sending them to CUDA, right? That's the function we use for that. But the mistake we were doing was we were directly using image.tcuda inside the model. And what this causes is this. Okay, let me explain this to you. So when I use this images.toCuda inside this, it sends the images into any empty space available inside the CUDA, not wrapped inside a variable, because I'm not wrapping it inside a variable. I'm just sending it to the CUDA. And when this iteration keeps happening again and again, what happens is the same value, the same image or any image for that instance that is passing on to the network goes into the CUDA into any empty space that is available. But we are never deleting this image, right? So what is happening is this image is stored in some garbage location that will not be able to locate because we haven't have a variable name assigned to the point. We haven't have a pointer to that image, right? The values where it is stored. So this information was lost somewhere inside CUDA, and whenever we were running new iterations, these values were getting stored inside CUDA again and again. So there was a lot of cache that was developing inside it. So that is what was happening. So to solve that, we basically use variable names where we always convert the labels or images using a variable name so that when the loop runs again, the same variable that points uh, towards that memory location inside the GPU where the images array is stored, access the same location using that variable, and then we access the information out of it. So when we reassign it, the same memory location is reassigned again and again instead of putting garbage values inside different locations. So that was the change that allows us to solve the CUDA memory error there. So these were the two major errors. And after that, we just wrote the training loop. Basically, it's generalized. That's how it works. And we obtained these graphs. This is the unconventional graph. You can see this is the first layer. This is the second layer. This is the third layer. Obviously, here we have. I know these peaks might not look like how the peaks were looking at the previous image that we just saw from our original experiments. But that's because I have used a moving average graph, because it made more sense. If I was looking at the known moving average graph, it was a bit too janky and the results were not clear at all. So this allowed it to be more readable. So that's why I did that. And this is the test losses for the unconventional, and this is the train losses for the unconventional. So you can again see the layers here, they are clearly visible. So yeah, this is what we did. So our non-conventional took 7.3 hours, and our conventional method training took, wait, print out somewhere. Yeah, I must have deleted the cell. Well, I can show you the results, I think. Mm, must have them here. Conventional, right? So, okay, thank you. So yeah, basically this was it. 27269 seconds. We calculated it using the Python time.time, and let's divide it by 3600, and you can see it took 7.57 hours basically. So yeah, we were able to save around half an hour using our method. So that was the basic insight into it in terms of time, and the graphs are already obtained. So these are the different results that we have available. Now what else do we have to do? Now we have to get results for the interpretability, or you can say the intermediate layers extraction of data, how they are compressing the data that is given to them. So the standard model, the standard convolutional model that we used for our conversion basically has 20 features, 20 filters in its first convolution layer, and we want to extract the weights from these features when we pass in an image. So how are we going to do that? Let's see. I'm not really sure. So first of all, we'll have to upload the weights here. Let's connect to a runtime. It's fine, it can be a CPU runtime too. It's not really necessary for us to use a GPU right now. And I have downloaded the weights here. So this is the final weights for our conventional method, and these are the final weights for our unconventional method. So I'll quickly upload them. And after that, I'll first let's write the code for our conventional one. Right. So, or let's just use a markdown, keep it more organized. Hmm. Okay. Let's also upload an image, any image. So to upload an image, what can we do? We also want to apply these transforms to the image. So uh, let's not use any image. We'll just turn the shuffle to off, and we'll use the image from our dataset only. Right. So how big is this? Oh, it is like this. Should it be a problem? What if I use a single image? How would that work? I'll apply the same transforms, right? Work. And I'll just pass into the model. Yeah, let's use a single image. This would be too much work. We can use anything. Let's use something that is more visible to the eyes. Yeah, like these kind of errors, right? These are more visible. So it doesn't matter anyway. This is just for what looks cool on the paper. I think this looks cool. So any image that multiple of these, just an artistic choice. Like it's not just an artistic choice actually. You also have to think about how uh, it would be visible in the intermediate layer. It should be something that has enough data that can be presented in the intermediate layer. Otherwise, it would be of no use. So I don't think patches is that great for it. So inclusions looked okay, but again, there's not much contrast into it, so it would be really difficult to interpret those layers. So I think scratches seem to be the best option then. Yep. Let's use this scratch. Or maybe this one. I don't know. Shouldn't be so much time. Yeah, let's go on with the fireworks one, right? That look cool. I hope I have not closed that one yet. Yep, this one. One look cool. So I'll save this image, then I'll upload it here. Download it. Why is it downloaded like this? Not in an image format. Wait. Not good. Save image as. Okay. .bmp. Yeah, because you need to have a file extension for it to work, right? Yep, this one works. So yeah, how do we get the results? So first of all, we'll have to apply the transformations because this. Let's first of all, our first task should be to input our image basically. So what we have to do is do this. Other than that, we'll also have to import torch and other stuff. So let's just quickly do that too. I think we'll need all of this, so no problem with that. And other than that, I think yeah, everything else seems in check. So these are the transforms. This is that. Now, how do we apply transforms? So basically, we have to open an image using torch. Torch using the data sets. I don't think we'll really be needing that. Oh, you know what would be simple though? What would be really simple? If I add a folder here, data, and I put the image inside this folder, right? So I should be just be able to call using this only. And just have one image. That's fine by me. I have no problem with that. So in the dataset dir is just data, right? And batch size should be one. Couldn't find any classes in the folder. No problem. Let's add another folder. What was this? Scratches. So now when I do this, I don't know why it keeps like this. It causes some problems sometimes. See, that's what happens. Must have created a IPM inside this that is causing the problem. And I still don't understand why this is not deleted yet. Oh my god. Why is it annoying? You delete IPM checkpoints. What the hell? Okay, fine, I'll do it like that. Let's see what folder it is in first. The data, then rm rf dot checkpoints, then come back to your original. Okay, now it should be done. Good. Wow. Now that works. Now we must have our image. We have the image in our data loader. Shuffle would not even make a difference because we just have a single image. So for let's do this now. Let's see how our image is looking. Convert all of this to. We don't need subplots because we just have single image again. Let's not do all of this. Let's just say count is equal to 0 and just plot dot I am shown. We don't even have a label, right? Or do we? Oh, we might have a label. It's fine. We can have the label too. Why is dot not? It is there, right? Plot dot set title, label dot item, and then lastly plot dot access. Don't need that, so this should work. Yeah, set title is not there, right? Because it's title. Set title is just for access. Yeah, okay, that works. Great. And I guess we don't even need these transformations. We don't need random rotation, random flip. We'll remove these and load all of this again. Yep, that looks better. That's our image. So that's our image basically. Now what we have to do is, after getting this image, now we just have to put this image into our model. So I'll just copy this. Now we are doing it for unconventional first. So yeah, this is the unconventional one. Oh wait, not the unconventional one. What is happening? Oh, this is the unconventional one. I mean the conventional one. Oh my god, what's happening to me? This is the unconventional one. Why I was defined steps here? I don't know. Is this where I have not defined any steps? Okay, this is it. This is our model. Right, this is the CNN classifier. Now, after doing this, we'll just have to. I'm so confused. You shouldn't leave your work in between. Becomes so confusing afterwards. Like, I'm not even sure what I was doing now. Just weird in that sense. But it's okay. We'll go through it. So yeah, so we'll have the classifier on now. Do we have TPU? No. So classifier is equal to classifier, and we don't need the device. So yeah, so that all works. So after that, don't even need an optimizer. Now we need to load our data, load our classifier mode. So let's do that. So every time I have to see this. I don't know why I keep forgetting it. So yeah, so it's just that. It's so simple. Oh, wow. Classifier, dot load state. in path, load functional classification 499.ph. That should be 8. Right, that should give our pre-trained classifier. Okay, I'll do that. Map location equal to torch your device. Now it's go. Actually, the pre-trained ones were on GPU, so I think that was the problem. So all keys match successfully. Great. Now we have our pre-trained model. Now we just need to get our output from it. So basically, we'll just do this. Output is equal to model images. Don't need step for the conventional one. This is the one, right? So weird. I must have. I don't know how I did it. Errors confuse you. So output would be our classifier images. Now, after doing this, what we need to do is, while getting output, we also have to get the like our conventional one and convolutional twos. Like what do they output? The X after them. So how can we do that? One of the simple ways is to do it like that, but that doesn't work. I was thinking of printing them basically, but that will not work. They have a very large size, so it will be truncated in the print, so that will not work. So how did we do it before? Totally. I'm shocked at how much I forgot. So yeah, I hope it is here. I don't think it will be here. I did not test somewhere else, but let's see. Yeah, the intermediate leader is not here, right? So how to access outputs after PyTorch intermediate layers? Oh wait, do I know this? Do I know this? Wait. I have one idea. So instead of getting the classifier's output, what if I say classifier dot con one? Right. Yeah, that works, right? So I have the output after the first layer. So output dot shape, it will all make sense after seeing the shape. So output dot shape is 1 comma 20 comma 36 comma 36. 1 here represents our channels, 20 represents the number of images, and 36 by 36 is, one must not be the channels, right? 20 are the channels, sorry. We have 20 channels, we have one image, one for one image, and these are 36 by 36 images. So how can we print them now? That's pretty easy. We know it, we have done this before. Here you go. Or we can just simply copy the for loop one. It will make our life even simpler because we have done all of this multiple times now. Yeah. So I don't know. Maybe I should even make a video series regarding teaching PyTorch. I'm not really sure right now. But let's see. I assume all of you know PyTorch already. That's why I don't try to go too much into the depth of it and just try to work on it. So yeah. So we'll need 5 by 4 now. So for I in range 5 and J in range 4. And we'll do the same thing basically. But instead of using this, we'll first of all say uh, let's make it simpler. Image is equal to output dot permute. So I basically want to replace the first and the zeroth dimension here. So I'll say 1 here, 0 here, and 2 and 3 I'll keep on the same places. Now I can access them like this. Right. I don't need a label anymore. There is no point in label. And So this should also work and everything should work. Next one is output out of dimensions. Why have I used image set? Okay. I don't need image set, no? I just need image. Can't call numpy on tensor that requires grad. Use torch.detach.numpy. Where have I used numpy? Or we can simply do I think this should also work. This works. So this is the output after the first layer. Okay. That doesn't really seem very helpful. Now, how do I make it even more helpful? Let's get the output after the second layer too, right? So output layer 1. Then here also we'll use output layer 1. Maybe we can even make it a function, just make it a function plot layer intermediate layer and output. So here we are calling this soul can go inside of this. And yeah, this should also work, right? Right. And we can now, what we'll have to do is plot intermediate layer and we can just call output layer 1. Output layer 1 is not defined. Now it is. And now it works. So now let's get the output layer 2. So how I'm gonna do that? I'm a simple guy. I'll use simple solutions. Classifier dot max pool. Before that we'll also use classifier dot max pool classifier dot activation, right? And before that we'll have to use finally activation dot con2, right? Yeah, so this should give us the output of the layer 2, which are 50 into 14 into 14. So now this would be not enough, so I should have also taken as input r I comma j. I is equal to 5 comma j is equal to 4 in standard, so I'll use I j, not even ij, that would row col col, so row col. Now this should be better. And here when we'll, so we have the output and after that we'll say plot intermediate layer output layer 2. We'll also say row is equal to, for 50 what should we use, right? 10 into 5. So yep, let's do it. And we have these two, so we can see these are decent actually, these are not that bad. But let's see how it is for our unconventional one. If we see any difference at all, maybe there is no difference. Maybe the difference was only visible for the fire dataset or colorful dataset, the datasets that are more complex. This is comparatively simpler dataset because it's black and white, that removes half of the difficulties. So basically to train this, we'll copy the model for layer wise training. Yeah, we'll just copy it here, run this. After this, we'll call it in the same way. No difference here. I guess the steps are also by default taken care of. If I remember correctly, step is equal to none, and it only behaves this way if step is equal to something. So by default, it should also work. Now, instead of loading these, we'll use unconventional classification 345 149 pth, and this should load it into the classifier one. And after that, if this is done, then we just need to do this one cell. Yeah, so this is after the first one for our unconventional one. Pretty similar actually. We'll look them side by side into a deeper detail later. And let's do the same for output layer 2. We should right above here. And there you have it. So this is for our unconventional one. Now you can see the differences in the layer 2, right? The level of blur there was there. It was visible. You can still see that the scratch is somewhere around here. This is the detail we are going for. Everyone has highlighted this in a different color, but you can see it is much more clearer here in every image. Like you can't see any image where there is too much blurred or not visible, or there is some random noise. You can still see the structure is kept and more intact. Now this is not very much of a difference again because it is simpler data, but we can see the differences in the time and accuracy itself, right? So yeah, I think the potential it provides for designing a neural network architecture is huge, because it takes less time for training, so it allows you to quickly see how much of a saturation loss you can achieve. And the traditional training might allow you to reach that result or somewhere plus or minus 1 to 2% of that result, not much away from it. So you will be able to test things in lower time. Other than that, by using this kind of interpretability in the graph that is allowed using the layer wise training technique that I showed you earlier, and this graph is basically what I'm talking about, these ones. So this is how a normal conventional graph looks, right? There is no training, there is no understanding of layers. Like you don't know how the layers are working at all, because it is all hidden inside of it, because all the layers are trained simultaneously. You don't know how each layer is behaving. But other than that, when we come to the graph of our training technique, we can clearly see that each layer can be interpreted much more easily, as we can see here. So that is basically the advantage. The advantage you get while designing a neural network is way better than anything else, according to my understanding of greedy wise layer wise training. Right. So that's what I understand from it, all of this. So these are also some good results in terms of accuracy and stuff, but I don't think this really matters when you come to the point that I'm keeping. And let me just correct it. This is the loss. I'm doing it from memory because I remember what it was. It is my paper after all. But yeah, I can ensure you that's so. Yeah, that's what has been done now. And now we have to move ahead of it. So we were able to gain these results. Now I'm thinking maybe we should get these results for some other data set too, just to ensure. So like maybe we can get some better images. We have used scratches for now. They have shown decent results, but let's do it for a couple of more, turning the shuffle to off, so that we have oh, we don't even need to turn the shuffle to off, right? Because we are directly using the image that is loaded here. So shuffle can also be true, bad side should be one. Yeah, everything works the same way. Let's just put in some more images into it. So let's create a new folder first. Tracing. And let's put one of each of them. Oh my god, these IPM checkpoints, man, I hate it. Tracing, and what else do we have? Let's keep saving this. So we have tracing, we have this, and what else? We'll also download this somewhere. I know it ditches you bad sometimes, So here's our data. There you go. Train, tracing, inclusion. We have already done scratches. Pitted patches rolled. Pitted patches. Wow, that's a tongue twist. Pitted patches. Finally rolled. Okay, so let's put one image into each of these, and we can download a folder, right? Oh my god, you can't. Okay, that's just so we'll use the first image of each of. Why not? 90. Yeah, that should be enough. Let's download this. Oh wow, now it works. Oh, I was doing it from here. Okay, that was done. So creating first image, inclusion first image, patches first image, fitted first image, and rolled first image. We already have scratches, but let's do it again just so that we have 99 of each of them. Cool. So let's delete our initial scratches. No one needs it anymore. And instead, let's upload. Oh my god, you're gonna create one there too. Hit you. We'll have to run the weird thing where it is. Where is it? Where I deleted that cell? Percentage CD data rmrf dot ipim checkpoints percentage CD patches rmrf percent dot dot. This should delete both of them. We go run this. Yep, that was good. So now let's start uploading. So increasing, we'll upload our increasing 99. In inclusion, we'll upload inclusion 99. In patches, we'll upload A99. It's all getting uploaded, right? In pitted, we'll upload pitted, pitted surface. Okay, that is also loaded. And in rolled, upload rolled surface 9. Patches will upload scratches 9. So much manual work, even after knowing coding. That's ridiculous. So yeah, that's all that's need to be done. Let's delete this again. No one cares for it. Now let's run all of this again. Let's see what we. I guess that was freezing. Can output the label too. I mean, we have the label, so okay, this is zero. So this is crazy. Yeah. So okay, here we can see a lot of information loss, and after the first layer, it is just chaos. Now let's see the unconventional results. The unconventional still used. Have I not run these? Where have I run? 45. Oh, okay, so this has not been yet. Let's see how the unconventional one works. So, I mean, that's equally as bad, equally as non-readable. I guess the image didn't have much data itself, so that should be it. Shuffling is true, so let's do this again. Okay, this time we got raising inclusion patches. This time we have got patches. Let's see how that looks. Okay, that also doesn't provide much information. I think these informations are retained here. Uh, I mean, the conventional one and the unconventional. Okay, the information you can see stored here, but still not a good result to show. So let's do this again. What have you got? Got the same. Okay, this is different. 4 is pitted. Oh no, 4 is rolled. That one. Wow, this is totally not readable. I mean, it makes sense. Let's see how the image is. Okay, yeah. I mean, you can see like it has retained much of the image, but still not make. Why is it normally distributed? Okay, this is one. This is inclusions. Let's see how these looks. So okay, these were the results. This is how it looked like in the second layer, and for the unconventional one, that's similar. And again, not a noticeable difference. Two, okay, so this is different. And they look very noticeable, like they have a high contrast. So I have high expectations with this one. Okay, so the conventional one just completely weirds it out. I mean, this was our image. There should be patches here. It's like a horizontal, like you can see a tilted smiley face here, right? Not exactly smiley, grumpy face, but yeah, a face. So yeah, that face somewhat visible actually. Yeah, and some of it is there. Now it is gone. I see some of it here. Okay, let's see the unconventional one. Yeah, you can see it is visible in more images. Right. This can make up for a good result. Like this has completely retained the original information, just compressed it. So this is good. Now I know it's not a good debate to say that the original information is retained, so it is a good working one. But here I'm just trying to comment on the human readability of it. So in terms of the original image and these images, these makes more sense. And if it is able to give the same level of accuracy, I think this network will allow the results to be more explainable and more readable. And that's the goal, to make more readable and explainable AI. So I think that's why this model seems to work better. So I think these are some good results, so we can keep them in mind. Now the one that is left is scratches 99. So let's quickly run this so that we land on scratches. Come on, don't be annoying. Yeah, here we have a scratch. Let's quickly do this. The scratch is the highest contrast one, right? You can see the scratch so clearly. Let's see how does that work. I think that would be same for both of them. It's just a line. Anyone can preserve a line. There's no problem in that. Both of them have worked the same. So I think the results that we are going to show is the patches one. That look most nice. That look the most. It's not just about looking nice for the research paper or something. It's just that it is the one that shows the difference between both of this. Now this is a simple task from a simple data set. We didn't want to complicate ourselves too much into the intricacies. That's why we used a real life task that has a standard model developed for it, that has been published, so we can debate that this has worked equally as well as the research paper. So this must be correct, right? So that's why we use this kind of data set. There is no other intention. So we'll just save these images now in our research paper folder. And yeah, we have all the results that we needed. Now what should we do? You want me to discuss this further? Like, I can discuss this further, right? We can discuss it from the start. We can discuss how we came up to this point. How can we go ahead in this? What can we do next? Or let's first save the images. That's the first task to do. Save image as. Let's go to the research paper folder. New folder. Intermediate layers. This images are input. After that, this image is our conventional layer 1. This image is our conventional layer 2. This image is our unconventional layer 1. This is our unconventional layer 2. Great. So we have all the results. That's what I had planned for this tree. That was it, right? Now we just need to compile all of these results and write a research paper out of them. That's the task for the next stream, right? We have to make a final draft of our result paper now that we have all of these results. So we'll do that in the next video. Yeah, that's it. Thank you. Thank you for being here. I know today we haven't discussed anything, and I know I'm feeling bad myself that we haven't discussed anything new, discussed anything cool, or learned something new. But we just had to get this work done. I had to discuss things that I had changed previously in the research paper that allowed us to write the code that actually ran and gave us the result, because in the previous team we were just stuck trying to write that code. We were getting some errors because of that GPU garbage collection thing that I talked to you about. So that's all of that happened. So now that we have these discussed, now we can work ahead after getting the first draft, final draft of our research paper done. Then we can work on something new, something better. That's what I'm into. I just really want to work into something new now. And this is done. I just want to get this done as quickly as possible now. So I'll just try to do that. I'll try to make some more videos of it so that we can quickly write this research paper and get this into the publication process. After that, we'll start working on our final draft. So after working on that final draft, we'll be working on our new projects, new research papers, new ideas, different topics, learning something new. We can make a PyTorch video from scratch and all of those stuff. Now I'm just boring you, I know. So yeah, bye.